Hey, welcome back to your favorite pre-calculus class. This is section 3.1, properties of linear functions and linear models. There's your objectives there. We'll talk about, first of all, a linear function. So any function of the form y equals mx plus b. Of course, your m is your slope, your b is your y-intercept. Just kind of reviewing this. For example, what if we were graphing this linear function? Again, you want to think about y. Oops. Get my pen here. About y equals mx plus b. Notice, first of all, your b, your y-intercept is 7. That would be the first thing you put on your graph, is your where it crosses that y-axis. It's 7. That's where it crosses your y-axis. Secondly, your slope, if you remember, is rise over run. And here your slope is negative 3. So make it into a fraction, negative 3 over 1, same thing as negative 3. So the rise tells you if it goes up or down. If it's positive, it goes up. If it's negative, it goes down. So this will go down 3. The run tells you if it goes right or left. Positive, it goes right. If it's a negative number, it'll go left. Again, this is the vertical change over the horizontal change. So down 3. Right 1 from that y-intercept. So I go down 2, 3, and right 1, and I put a dot right there, maybe a dot if it'll let me, and down 3, right 1 again, put a dot. You could keep drawing this thing, and there's a better picture of it right here. Notice they went down 3, right 1, okay, from that y-intercept of 7. Alright, let's use average rate of change to identify linear functions. If you remember, average rate of change is the slope. So on that equation we just worked with, your slope was negative 3. And notice if we ran the slope formula each time, so we took the y2 minus the y1, you see the 10 minus 13 over x2 minus x1, so we have 10 minus the 13 over negative 1 minus the negative 2, you end up with negative 3 over 1. So your slope is negative 3 as shown right there. And then you do it for the next 2 points. You notice your slope is negative 3. Every time you take a couple set of points, your slope is always going to be negative 3. Your average rate of change, your rate of change is going to be negative 3. So that's what's going to happen with a linear function. You're going to have a fixed average rate of change for any sort of linear model. So we're going to determine whether these two situations with their data are linear models. Okay, so this first one says a strain of E. coli placed in a petri dish at 30 degrees Celsius allowed to grow. The data that's on the next page is collected. The population measured in grams, time in hours. Plot the ordered pairs and use the average rate of change to determine whether the function is linear. So here's the data. Notice your time. So at time 0, you're starting out with 0.09 grams. That's your population. An hour later, now you got 0.12 grams and so on. Here's your ordered pairs, right? And so what we're trying to determine is this thing linear or not? So what you want to do is we would start with these two right here, and we would find their slope. And you say, well, y2, 0.12 minus y1, 0.09 over x2 minus x1. This ends up being 0.03 over 1. So slope is 0.03. And then you do it for the next set as well. Let's find this slope and see if it's the same. It's got to be the same. y2 minus y1 over x2 minus x1. But this time it's 0.04. So your slope here is 0.04. As soon as you see it change, it wasn't 0.03, it was 0.04 this time. Right? As soon as you see it changing from 0.03 to 0.04, and notice it keeps changing, okay, you throw it out and you say it's not linear. And notice the data here is not linear. It's not following a linear pattern. It's not a line. All right, so here's your second scenario, and going back to our explanation here, let's Read it here. The data in Table 3 represents the maximum number of heartbeats that a healthy individual of different ages should have during a 15-second interval of time while exercising. And we're going to determine whether this is linear. Okay. So there's your age, there's your maximum number of heartbeats, there's the points. So we're going to start out, use those two first. So y2 minus y1 over x2 minus x1. So 47.5 x2 minus x1. Anyways, you go through and you find the slopes of those two, then you find the slopes of those two, and so on. And what you notice is the slope is negative 0.25. With the next 2 points, the slope again is negative 0.25. The average rate of change, negative 0.25 every time. So we can conclude, yes, this is a linear function as displayed with the graph there. You can see it has a linear pattern to it. As the age increases, the max number of heartbeats in a 15-second interval is going down. Okay. Now let's determine whether a linear function is increasing, decreasing, or constant. Well, it's kind of nice with these linear functions. Okay, let me go back to this for a minute. Since we got a line, if we have a function, let's say this is 2x plus 1, you notice it's increasing, in this case, throughout its whole domain. Throughout the whole domain, this thing is increasing. Why? Because the slope is 2. It's going up 2 and over 1 every time. Up 2 over 1, up 2 over 1. Whereas if you have a negative slope, right, if you have something negative slope, now you're decreasing. Okay. And finally, if you have a line that like y equals 3, where your slope is 0, that would be a situation where you're constant. Okay, so the slope is the big giveaway on those for linear functions, whether it's increasing, decreasing, or constant. So you look at this first one, you got 5x minus 2. You say, well, without graphing this thing, is this thing increasing, decreasing, or constant? You say, well, my slope is positive. My slope is 5. So this thing's going to be increasing. Whereas over here, my slope is negative 2. This one's going to be decreasing. Right here, my slope is 3/4, increasing. And finally, you got this constant y equals 7. The slope is 0 here. Notice it's 0x. They don't write 0x in, but your slope is 0. All right, this is y equals 7. That's what it looks like. So this thing is constant throughout its domain. All right, let's get into building some linear models from verbal descriptions now. So here's your slope-intercept form of a line. We're going to be modeling using that form here. Here's an example with straight line depreciation. So you have book value. It's a value of an asset that a company uses to create its balance sheet. Some companies depreciate assets using straight line depreciation so that the value of the asset declines by a fixed amount each year. So let's suppose a company just purchased a fleet of new cars at $31,500. The company chooses to depreciate each vehicle using the straight line method over 7 years. Okay, write a linear function that expresses the book value of each car as a function of its age, x in years. So if you can kind of imagine for a minute, you've got this, these cars worth $31,500 initially. This is the value. This is x in years up to 7 years. So at the end of 7 years, they've depreciated it down to 0. And each year, if you notice, they're losing $4,500, so it's going down $4,500 for each year over. For each year, okay? So what would the equation? First of all, part A, write a linear function that expresses the book value of each car as a function of its age in years. So V of x, the value of the car after x years would be, well, it's starting out at $31,500, so there's our y-intercept, and it's losing, so negative 4,500x for each x year. And you could check that, you know, for year 0, if you throw 0 in for x, you would end up with $31,500. Right? After 1 year, you would end up with $27,000 if you put 1 in for X, right? Negative 4,500 times 1 plus 31,500 leaves you with $27,000 after year 1. And you'd get down, if you put 7 in, finally you'd end up with a value of 0. So part C, what is the book value of each car after 3 years? Well, you just throw a 3 in right there, and you get your solution shown right here. After 3 years, throw 3 in, you get $18,000. Go back to the question. Let's interpret the slope. So the slope here is saying we are losing $4,500. Losing $4,500 for every year that the car ages. Okay, that's what your average rate of change is saying here. Finally, part E, when will the book value of each car be $9,000? When will the book value, so saying at what X, right, how many years later will the value be 9,000? So we got to let V of X be 9,000, and then we solve that. V of X be 9,000. Let V of X be 9,000. Now you're solving this right there. Okay, so subtract 31,500, divide by negative 4,500, and it's 5 years later that it'll have a value of $9,000. Okay, here's a nicer graph of what's happening here in this linear model. Alright, let's talk about supply and demand. So quantity supplied of a good is the amount of product that a company is willing to make available for sale at a given price, whereas quantity demanded is the amount of a product that consumers are willing to purchase at a given price. So let's suppose here the quantity supplied, S, and the quantity demanded of widgets are given by the following functions as a function of the price. P is the price in dollars of a widget. Alright, so we're building widgets. S of P is the supply based on the P price that a company is willing to make available. D, demand, which is the demand based on the price. Okay, so first of all, the equilibrium price is when the supply meets the demand. And the first part here, when is the equilibrium quantity? The amount demanded at the equilibrium price. And so you would set the two equal to each other and then solve. Find that P and then plug that P back into S. S of P or D of P. Okay. And then we'll also do these portions here next in just a second here. So let's start out with this to find the equilibrium price here. So we'll set S of P equal to D of P. So notice S of P there, D of P right there. Solve that thing. So you add 200 to both sides, you get 1200 right there, add 20p to both sides, and soon enough there's your equilibrium price. So that's when your supply equals your demand price, $20 per widget. Okay. Now you want to find the equilibrium quantity, so the supply, right? You plug that 20 in to the original 40p minus 200 model. Okay, so plug that in and you get 600. So that's your equilibrium quantity. And it would also be the exact same as the demand. Okay, because that's where, let me give you a picture of that. That's where they meet. That's your equilibrium point right there. You see it there? 20. P price of 20. Okay, let's go back to the problems here. Now part D. When is the supply greater than demand? What determine the prices for which the supply S of P would be greater than the demand? Let me go back to the visual of this for a minute. Can you see here's your supply, right? Notice that your supply would be higher than your demand down here anytime P is greater than 20. All right, whenever that price is greater than 20, that's when your supply will be greater than your demand. So your algebra on that is you just take your supply, a little greater than sign there, greater than your demand. You solve that thing, and it'll give you the price for which that will occur whenever P is greater than 20 on that. Okay? That's when you'll have the excess widgets on that. And then finally, the graph of that, graph those two linear models. Okay, well, thanks for watching. Hope you learned something today. We'll see you soon in class.